After those two talks that first summed up a bit the history of this p-value, how the science is done today, what p-value actually is and is not, we thought that it would be maybe a bit reassuring and probably more of a positive message if we provided you with things you shouldn't do, and most importantly, things that you should do if you want to draw conclusions correctly when using statistical models. And this means that, so this includes using the p-value itself, but using it properly, and also using additional information in order to be able to draw a good conclusion. So first of all, what not to do. So I have one slide to tell you what you actually shouldn't do. What you shouldn't do first is present the p-value like this. So be it a p-value more than a given threshold, or under or above even a higher threshold, or below a given threshold, or below or above any threshold. Recommendations now are that you do not present the p-value as being more or less than a given threshold. This includes avoiding to present a p-value in this form, for instance, which is very often seen in tables where you have, for instance, a difference between two means, and then you have a little sign, an asterisk, saying or referring to different thresholds and p-values being more or less of those thresholds. So we recommend that you do not do this because p-values are a continuous measure of the incompatibility of your data given your null hypothesis. So then the second recommendation is to stop interpreting your results solely based on the p-value. And this we have said it repeatedly throughout the two talks, and you're going to hear it from us repeatedly if you come to us for help in your statistical analysis. We wish that you do not base your conclusions only on the value of the p-value, and certainly not whether or not it is above or below a given threshold. This, of course, means that if the p-value is above the conventional threshold of 5%, you do not conclude that there's no association or there's no effect. Because you'll see that this might not actually be true. I mean, we need way more information to conclude about whether or not there is a true association or there is a true effect. It might only tell you whether your data is more or less compatible with the hypothesis that there's no effect or no association, but it doesn't actually mean that there is no effect or no association in the real life. And this, in turn, has consequences on how you phrase your conclusions. And we tend to be, we generally want to be a bit strong in our conclusions. We want to convince people, as it's been mentioned in the questions, editors or reviewers like to read strong conclusions because they think that then their audience, their readership will be more convinced, and they will come to their, they will read their journal with more enthusiasm. So we tend to use sentences like "we prove" or "we disprove" that, or a given hypothesis or a given mechanism. We demonstrate the existence of a mechanism. Our results may validate or invalidate a given hypothesis, or we confirm previous results or previous studies. And we would like you to stop using those strong words, and we're going to offer alternatives that are more reasonable, we think, without necessarily weakening your main message in the end. So those are for the don'ts. And most importantly, amongst the don'ts, and that's more a part of the ethics of science actually, you do not want to go fishing for a significant p-value. You do not want to selectively report results based on those p-values, like talking only about the significant result, disregarding the non-significant results. And this, of course, holds not only for your publications and reports and papers, but also within those reports, it is important that you right away from the abstract that you do not give a you do not mislead the reader through a strong conclusion, basing your abstract only on those significant results. Of course, sometimes it's a bit difficult because space does not necessarily allow for nuances, but it's important to try to keep this in mind. All right, now what do we do then? If we can't do all this, what do we do? Well, first, I mean, it's been said already several times, we have to accept uncertainty. We have to accept the fact that even though we put our best in designing very strong and very efficient and very well-designed experiments, we do not exactly know how it works, how the world works. We have to state hypothesis and test hypothesis, but it only takes time and reproduction of experiments to be able, in the end, to draw firm conclusions. And you can't actually draw firm conclusions based on one single study. And you have to accept that the result of this study is going to contain some uncertainty. So first of all, use the p-value as a continuous indicator of the compatibility of your data with the null hypothesis. And the null hypothesis includes many things. It includes an absence of an association, an absence of a difference, but also your actual sample. Does it reflect what the overall population actually is? Is it actually your target population, or is it a biased sample of your target population? Have you used the proper statistical model? And sometimes it's not easy to choose between different statistical tools, and even trained statisticians sometimes do not agree on what type of tools they should use for analyzing a given set of data. And then there are alternatives to p-values. For instance, it's been one of them that has been proposed is called the Shannon information value, or also the surprisal. It's a very simple index calculated as minus the log with base 2 of the p-value. And this actually reflects how surprising a result is considering the null hypothesis. And so how to use it, let's imagine that you define k as the nearest integer value to the s value, and your result is as surprising as getting all heads on k fair coin tosses. So let's give you an example. If the p-value is 0.055, so slightly above the dramatic 5% threshold, S is slightly above 4, K is then 4, and the result is no more surprising than having all heads on 4 fair coin tosses. So if you have already tossed coins, this might happen that you end up with 4 heads. It's not unreasonable. It's not that rare. Let's imagine that the p-value now is slightly below the dramatic threshold of 5%. S is slightly above 4.4. K is still 4, and you basically have a result that is virtually the same as the previous one. So your result is no more surprising than having all heads on 4 coin tosses. So it's not that surprising. This happens. Then let's imagine something that is a bit further away from the 5% threshold. P-value now is 0.03. The S value is around 5, K is 5, and then your result is no more surprising than all heads on 5 fair coin tosses. So, okay, a little bit more surprise, but not that much. I mean, no one would actually think that the coin is biased just based on such a result. Of course, you have values of p-values that might make you think that the results are indeed surprising, considering that, for instance, in this case, an S value close to 9 gives you a K of 9, and then the result is as surprising as having all heads on 9 fair coin tosses, which then becomes way more surprising, although not impossible. And this also you have to keep in mind. Then another recommendation we can give you, apart from using p-values as a continuous indication of the compatibility of your data given the null, using the S value to give you an idea of how surprising your result actually is, well, you could use what are generally called confidence intervals, but not as confidence intervals, but rather as compatibility intervals. And as Michael already mentioned, those compatibility intervals give you an indication of the value of the possible values taken by your estimate. So you're looking for the true value of your effect, and you compute a point estimate and a compatibility interval. And this 95% compatibility interval tells you that those values within those two limits, the lower and the upper limit, are all compatible to some extent with your data. So, of course, you're interested in the point estimate, which is the most likely value given your data, but you can't disregard the two lower and upper limits, because the values given by those two limits are also compatible with your data. And this is very important to keep in mind, because this is how you're going to introduce some uncertainty and some nuances and moderation in your interpretation of your results. So what else to do? Well, actually, we recommend, and it's not only us, it was part of the ASA statement, to be thoughtful about your data. I mean, you have expertise. Similar study might have been conducted in the past, or similar experiments, or anyway, data that has been collected in some way or another that might give you already some hint about what's going on. And interpretation is not only about the p-value, it's also about the estimate, the compatibility interval, and what you might already know of what is actually going on. And so we recommend that you use the point estimate, the confidence interval, and that you also represent your result in a way that will help you to understand what actually is going on. For instance, by using graphics to present your data with a mean, median, or odd ratio, risk ratio, and a compatibility interval. And this is, for instance, an example of how your data might look like and how you will then interpret such results. Let's imagine different effect sizes. Those might be, for instance, differences in group means. So you have, let's say, two groups with two means, and you have the difference between the two means. And you have several scenarios, so 5 different scenarios, where you have 5 different estimates of this effect size with an associated confidence interval or compatibility interval and an associated p-value. So in the first case, in the case of the scenario A, you have an estimate that says that the effect size or the effect is most likely positive and large with reasonable confidence, all right? In the scenario B, the effect is most likely positive and large, but possibly the compatibility interval tells you that it could also be very small negative, or it could be null, or it could be very large positive. So suddenly you have way more uncertainty. So you have a point estimate that tells you that it's potentially large, but you have a lot of uncertainty. So the compatibility interval tells you that a small negative value is also possible. for instance. In the third scenario, the point estimate tells you that most likely it's small or the positive, but it could also be large negative, it could be null, it could be a large positive value. So again, a lot of uncertainty. You have some suspicion that it is close to zero, but there's so much uncertainty it's going to be difficult to conclude. In the fourth scenario, you have most likely a very small positive effect, but possibly a small negative or a null effect. You have some uncertainty. And the last scenario is with a bit less uncertainty. You have a most likely very small positive effect, and apparently it is not null. So you have some indication that the effect is positive but small, and this will have consequences on how you actually interpret your result, because this is not the end of the story. Now, once you have a kind of a statistical interpretation of your effect, you are biologists, you are physicians, you're doctors. What really matters is whether or not this makes sense in your practice, whether this makes sense for understanding the world. So in the case of the scenario A, you have potentially a large biological effect. That's a potentially important effect. You have some uncertainty, but you can be relatively confident in saying that given your data, given the compatibility interval, given the point estimate, if anything, the suspected effect has to, or is likely large and likely relevant and important. It's something we have to account for in, for instance, a medical practice. In the case of the scenario B, well, potentially the effect is biologically important, but it's largely inconclusive because we lack precision. And we might lack precision because our sample is too small, or our measure suffers from a lot of error due to simply the technique, for instance, random variation in a PCR result or in the amplification or whatever, or a reading of an optical density. This happens, this is not necessarily linked to the sample size, it might be technical issues. What really matters here is that you potentially have detected an interesting effect, but you lack precision, and the only solution to this is to either or increase your sample size and increase precision in your measure. The third scenario now, well, basically it's inconclusive due to lack of precision. What does it say? Statistically, it says that your point estimate is close to zero, but there's such a large compatibility interval that tells you that any large value or any large positive value or any large negative value is actually compatible with your data, so you can't conclude anything. This is very frustrating, but this happens, and I think you have to be fair and transparent about this. It's important. In the fourth scenario, well, then you have a most likely unimportant effect. Basically, what your point estimate says and compatibility interval says is that your effect is potentially small. You have some uncertainty around it, so that potentially it's null, potentially it's positive or small. In any case, it is most likely an unimportant effect. And in the last case, you can be a bit more firm or a bit more confident in saying that you have good precision in estimating your effect. Potentially, it will turn out to be significant, but truly, how important is such an effect? It is biologically irrelevant, although statistically significant. It's so small that it's potentially irrelevant, and this is important also to bring this into the discussion, and you see now that if you base your conclusion interpretation solely on the p-value and whether or not it's above or below a given threshold, this is only part of the information, and it makes no sense to make a strong conclusion based on the p-value when actually you discuss a very small effect that has no implication on your medical practice. So in the end, and this has been also said by my colleagues, we recommend that you are also open and transparent when you report your results. And this can be done through several different tools. Well, first of all, and this is a practice that is now being generalized in many disciplines, not only in medicine, but in other disciplines of biology or physics. The fact that you can pre-register or even publish your study protocols. And by doing so, you make sure, I mean, this is one way of first working on what exactly should be your study, what is your outcome, is it a good outcome, is it the actual target outcome, is it the target population? So you discuss everything a priori, you define a protocol, and then you stick to it. You will be less tempted then to go hacking and fishing for extra results that come up with significant p-values and try to sell those instead of the original actual question. So pre-registering can be done in several websites. There's one here in Switzerland to register studies done on for research in humans, on humans. There's one that is linked to the US government. And you can also pre-register your studies in protocol exchange. And as I said, I mean, you can also publish your protocols. Maybe some of you have already done it. And several journals offer a way or means to publish protocols in their issues. Even Nature actually has a journal that offers to publish protocols. Another way to be transparent and open is to, together with the pre-registration and publication of the protocols, is to write a detailed statistical analysis plan. And this is what we do here at the CTU. Whenever you come to us for help in analyzing your data, the first thing we do is to plan a statistical analysis, defining your outcome, your study population, the data sets, dealing with anything that might make the interpretation a bit more difficult, like dropouts, missing values and everything. How do we deal with all this? How will they impact your interpretation and your results? And we deal with all this before we actually do the analysis and before we actually have the data. Then, once you have your manuscripts, you can also preprint your manuscript, and you can open this to your peers. So to have some feedbacks, everyone then can check whether you comply with the protocol that you might have pre-registered, or with you could also actually preprint your analysis plan. And you can do this on several platforms. One of the most known platform is medRxiv. By doing so, I mean, the idea, so you can preprint your manuscripts, and we also recommend that you report full results, including in the abstract. So not only reporting the few significant results in the abstract to appeal to readers, but try to find a space to also report potentially more disappointing, but actually results that do contribute to knowledge also in the abstract. And then share your data. I know that this is not a common practice in the medical world. It has become a very common practice in other fields of biology or other fields of science, like physics, for instance. And it's also becoming a general recommendation by funding bodies. The SNF, for instance, in Switzerland recommends that your data is shared when published. More and more journals actually ask you to share your data once the paper is published. And the idea of having an open science is now developing to the extent where when you get a grant from the SNF, well, at least in some fields of science, you have to favor journals that openly publish your results and offer a way to share your data and share your publications. They even grant you money to pay for the actual fees of publication fees when you want to make a paper open to everyone. The benefit of sharing your data has been have been well listed in a recent paper published in Nature, trying to promote this approach in opening science, and many platforms offer the possibility to actually share the data. So I'm not going to go through all those platforms, but several of them exist. Some are free, for some of them you have to pay a small fee. But again, if you get a grant, for instance, from a funding body, you can ask for some money to then upload your data on one of those platforms. So it's no longer an excuse not to have the money for this. And I think it's no longer an excuse to say that, well, we generally don't do it because now it's going to be more and more requested by those funding agencies. The European Union, for instance, has a whole platform to share a lot of data, and it's very interesting. You can actually find very interesting data there, especially lately concerning the COVID outbreak. Another recommendation is try to be modest. I mean, we tend to oversell our results. I mean, I understand why. I've been in research myself. And it's true that as a young scientist, very often your career depends on whether or not you publish significant results. But I think there's a way to be more modest about our research and the way we do science. We have to admit when our data cannot allow for a clear conclusion, and we need to leave it open. It's very important. We have to say that our data is consistent or inconsistent rather than prove or disprove a hypothesis. It agrees or disagrees rather than confirms or doesn't confirm a result. And so we're consistent or we agree with previous hypotheses, previous results, but we have to be a bit more modest. And we have to allow negative results to be positive contributions to knowledge. And this is very important. It's very important for several reasons. I mean, you've seen those two slides before. This behavior is still too often seen, and this is a true problem because when you want to assess the actual size of an effect, the actual efficacy of a treatment, you have to base your decision on several studies, and you have to include negative results if you want to have a fair and accurate estimates of the actual effect size, of the actual efficacy of a given treatment or a given compound. All right, so with this, I'm done. I want to thank you for your attention, and I think we can open the general discussion soon. So the word is back to you, Sandra.